The choice between high quality and budget bearings often comes down to assumptions about performance. But how much of a real-world difference do these premium bearings actually make? This video is all about getting to the bottom of that question. Knowing this will help you make informed decisions about your robot builds, ensuring you're getting the best possible performance where it truly matters and not just chasing a higher price tag. I'm Coach Pratt, and I've spent over 10 years as a robotics and design educator. I've coached national champion FTC teams, earning multiple Inspire awards, so I've seen firsthand how component choices impact outcomes. In this video, I'm going to run you through a series of direct experiments. We'll be testing high-quality bearings against their low-cost counterparts on linear slides to see the raw performance data. We'll compare them side by side so you can clearly see if, and by how much, more expensive bearings actually outperform the cheaper alternatives. Let's get started. So I've got two different V-groove bearings here, and I want to take a closer look at what separates a high-quality bearing from a lower-quality one. Now, right off the bat, it's important to note that these two are not identical in size, and that's going to play a little bit into how these things feel and perform. This one is from GoBuilda, and we're going to consider this our high-quality example. It's 6 millimeters thick, it has a 10.5 millimeter diameter, and it has a 4 millimeter inner diameter where you put your bolt through. The V-groove itself measures at about 8.6 millimeters across. The other bearing, our low quality, is from some random supplier on Amazon. It's only 4 millimeters thick, it has a 12 millimeter outer diameter and a 3 millimeter inner diameter, and its V-groove is about 9 millimeters across. In practice, despite these two bearings being different sizes, because the V-groove section, it runs on a so close from about 9 millimeters and 8.6 millimeters, this really shouldn't affect our test results all that much. Now let's talk about what you can immediately see and feel. Looking closely at the V-groove bearing on this higher quality from GoBuilda, the machining itself is quite clean and the surface is a lot smooth. When you give it a turn in your hand, it feels a lot more fluid and there's minimal grittiness. There's very little side-to-side play inside the bearing itself. And the inner race, so if I hold that inner race and I move it in my hands, there's basically no play at all. And that's the same for axial. That's movement in and out itself. I'll compare that with our lower quality bearing. You notice that the finish of the groove itself, isn't quite as nice. And if I spin this one, it can catch a little bit in my hand, doesn't spin quite as smoothly. There's also quite a bit of play in between both radially and axially up and down. Beyond what's immediately obvious, the internal difference between these two are huge. High quality bearings typically use better grades of steel for the races and the ball bearings themselves. The balls are more perfectly spherical and they're more matched in size typically. The cage typically holds the balls apart. It's made from a better material, designed for lower friction, and it may even have a full complement of balls that has no cage inside. Although in these really small sizes, they're almost likely guaranteed as a cage. Manufacturing tolerances are also typically quite a bit tighter and high quality. Everything just fits a lot more precise. Lubrication is also another good factor. This good bearing likely has a quality lubricate that's sealed on the inside of it. The cheaper bearing, typically what they do is there's no lubricant at all, and they just rub grease all over it. So there's actually grease all the way on the outside of this, rather than actually being packed inside the bearing itself. Using that grease versus different lubricants definitely affects how long it will last and how fast it spins. Sometimes those low-quality bearings can even feel a little bit dry or even sticky when they come out from the factory. But in practice, how much do these differences actually really matter? This high-quality bearing is almost 4 times the price of this low-quality bearing. So if you want to pay 4 times the price for this bearing, is it actually worth it? Let's go take a look at some real-life tests. So this is a double-strung lift here. Effectively, what double-strung means is on each pulley, you've got both the extension and the retraction string wrapped up through the pulley itself. So coming off the spool, the extension goes through this pulley, this pulley, this pulley, this pulley, this pulley, until it eventually ties off here. And the retraction goes through this pulley, this pulley, this pulley, this pulley, this pulley, this pulley, but it eventually ties off to the traction string. So in comparison to a double strung system, you could run your system with the retraction string not going through the system. So your extension string still runs through the system and ties off, but your retraction string simply gets from the last point and it just goes straight down to the motor. Looking at the mechanical setup here, I have 3 Misumi SAR 330s connected together on a continuous rigging on the extension and retraction string are running on the same adapter. Next is pulley. I've got a 1-to-1 gear ratio using some acetyl gears so that when I go to replace the motor, I don't have to actually replace the pulley and restring my slides every single time. On the top bar here, I have a quick little bar here with a few different zap straps attached so that I can grab weights of different sizes. These are 1 kilogram weights and the small ones are 500 grams so that I can move up in 500-gram increments and load that somewhat balanced across my system as we move up and down. For the electronics, I have 2 different LEDs. One is a green LED, one is a yellow LED. The green LED looks at the extension section and the yellow LED looks at the retraction section. The green LED will turn on when retraction has started and it will turn off when retraction has met its max height. Same thing for the yellow. It will turn on when retraction has started. It will turn off when it's met its base level. To know when my extensions have reached the bottom, I'm using the encoder that's attached to the motor here, and then everything is controlled off of a button toggle switch. Lastly, to keep track of our cycle times, I've got a tracker here that tells us what our extension time was, what retraction was, and then as well as what our cycle time was. I'm just using time monotonic to do that as we're running through our motor encoders. So if I were to run this in a full cycle, I would tap the button. Green LED turns on, turns off when it's up the top, brings it back down, turns on bottom. There is a 300 millisecond pause at the top, and that is a counter for in the cycle. Last things to confirm, I'm using a fully charged battery here on a RoboClaw 12-volt 30-amp microcontroller. The battery I'm using is the same one that is legal in FTC, so you can be sure that this data is always going to be the same, and it should be pretty applicable for you based off of your tests. So let's go get started. Okay, so I've got the 435 motor hooked up on here now. Got a reprogram for the new encoder positions, and let's get a look at the baseline. I've also taken and swapping out a brand new battery so that we're nice and charged at 13.2 volts. So let's take a look at what the baseline is. So it looks like we're sitting about 2.04 seconds as a baseline. Let's go ahead and add out half a kilogram, see what that gets us. Pretty good, added about a tenth of a second. Looks like we're averaging about 2.12, 2.13. Let's swap that out for a kilo. And we're a mighty consistent 2.25. Let's go for a kilo and a half. Pretty big slowdown on that one. 2.38 is our average. Let's go up to 2 kilograms. You could really hear the motor starting to work on that one. Okay, we're sitting about 2.57 on average. Let's go up to 2.5 kilograms. You're looking at about 2.88, 2.89 for an average. We'll see if it can even lift 3 kilograms realistically. Let's give this a test. Ooh. Looks like you're probably going to max out about 3 kilograms on a 435 RPM motor. You're sitting at about 3.28. I don't know if I want to run that too many times just because of the just how slow that got. So let's keep moving up. All right, so we've got a fresh battery installed. We're now looking at the 435 motor, but we're going to do the dual strung method on the high quality pulleys. Let's go ahead and get a baseline and see what we're looking at here. Okay, looks like our baseline is about 2.07, 2.075. Let's load up 500 grams and see what that does. Okay, we're looking at about 2.1 seconds on 500 grams. Let's go up to a kilogram and see what that does. Okay, we're looking at about 2.12 on average with a kilo. Let's move up to a kilo and a half. And we're averaging about 2.21 seconds on a kilo and a half. Let's move up to a full 2 kilograms. Ooh, 2 kilograms, you really start to hear this thing struggle. You're sitting about 2.36, 2.32. Let's do one more to get a little more consistency. Okay, 2.31. So let's call that about 2.32. Let's move up to 2.5 kilograms. See what this goes. We're going to do this one once because it's really starting to struggle. And you're sitting at about 2.53. And let's go up to the full 3 kilograms. And you're sitting at about 2.88 on the full 3. And you notice it was really struggling to even hit that top point on the extension as well. So definitely would not recommend 3 kilograms on this dual strung system. Let's go ahead and check out the next motor. So now let's take a look at the single strung system where the retraction string does not loop through all the different pulleys. And let's see if that makes any difference across all of our baselines here. Okay, looks like we're averaging about 207, 208 on a fresh battery. Let's add up 500 grams, see if that makes a difference. You really have to make sure that you get your string well aligned. Mine's clearly not perfectly well aligned, and that's able to get hung up on one of these systems here. So let's do that baseline again. There we go. Okay, so you're looking at 213 both times across. Let's move up to a kilogram. Okay, about 214, 216, so let's say 215 in between. Let's move up to a kilo and a half. Okay, we're looking at about 222. Let's move on up to 2 kilos. Look at about 229. Let's move our way up to 2.5 kilograms here. We're looking about 2.4, and let's move up to our full 3 kilograms, is where about we maxed out on the double string. And we're at about 271. Okay, so we're now at the 435 RPM motor. We're doing this single strung system on the high quality pulleys. So let's go ahead and get a baseline here and see what we're getting for our movement. Okay, we're looking at about 2.01 seconds. Let's move up to 500 grams and see what we get. We're looking at about 2.04 seconds. Let's move up to a full kilogram and see what we get. About 2.1 seconds. Move up to a kilo and a half. So about 2.17 seconds at 1.5 kilograms. Let's move up to a full 2 kilograms. You really start to hear it move at about 2 kilograms. Look, about 2.3, right on the dot. Let's move up to 2.5 kilograms. Well, it's really struggling to get up now. Look, about 2.52 seconds. And we're going to the max of our test today, the full 3 kilograms at the 435 motor. And you're looking at about 2.88 seconds. Did look like my retraction string fell off on that one, so let's go ahead and try that one more time. All right, let's go ahead and try that 3 kilograms. Again, we know this thing really struggles. Just do that once. And we're sitting at about 2.81. Oh, and so much weight on my system, it's broken my top pulley. So it looks like that's the last test we're going to do on the 3 kilograms. And let's move on to the next test. So I'm using PLA as these tests. This is a great reminder of why you should use PTG, because PLA likes to break catastrophically on these points. So it will snap the piece right away. Now, would this have happened had this load been balanced out on the second side? Likely not. But again, you're probably not going to be running 3 kilograms and smashing it down onto a hard point where you're going to have all the shock going through your system. This is the 1,150 RPM motor. I've swapped out a new battery. I've got our encoder reprogrammed to our new start and stop points. So let's get a baseline started here. Oh, wicked quick at 1150. We're looking at 0.86 seconds cycle time. So under a second, that's pretty impressive. Let's see what we can do when we add on 500 grams. Oh, throws our weight to the ground. Nope, throws it to the ground again. Let's strap that on so we don't lose that. There we go. Let's try it one more time. Oh, that is quick. So we're looking at average cycle time about 1.14 seconds. Let's see how it does with a kilogram. I'm going to knock that off. Throw on a kilogram. I think it's going to struggle here with a kilo, but let's see. Ooh, quick at the bottom. Oh, yeah, that's real quick. Real quick. In fact, we actually shattered off our zip tie there so much. So we're looking at about 0.3 seconds to come down, because that is looking a little bit off, but that's because it takes about a 1/4 second pause at the top. And because it takes that pause at the top, this is already starting to fall down when the motor is not powered at that point. So realistically, if you're not actually providing power to this motor, it's always going to be dropping it down. So now let's take a look at the 1150 RPM motor with a high quality bearing on the dual strung system. So let's go ahead and get a baseline here. And it looks like your baseline of about 0.74 roughly, 0.73 perhaps. Let's go ahead and load up 500 grams. And let's see what we get on 500 grams. Okay, we got 500 grams loaded. Let's go ahead and take a look at what this does. Okay, we're looking at about 0.79 on average. Let's go ahead and load up a kilogram and see what that does. All right, so we got a kilogram loaded up. Let's go ahead and take a look at a kilogram system. Okay, I'm only going to run that kilogram once just because it really does not like slamming down on about a kilogram, because I'm only supporting this on one side. Let's go take a look at the next motor to test. This is now the single strung section on the 1150 motor. So let's go ahead and get a baseline. Looks like our baseline is about 0.85, 0.86. This is with a fresh battery, by the way. Let's go ahead and put up 500 grams. As you learned last time, this thing likes to fly off, so we're going to go ahead and tie this down so that she can't go flying off. All right, so let's take a look at 500 grams. Let's let it balance out. Okay, it looks like we're averaging about 0.95, 0.96. Let's move up to a kilogram. Okay, let's take a look at a kilo. Boy. Okay, looks like we're only going to average about one test on that one because we have shattered our mount. Make sure you're using PETG on these. This is just a PLA one, and it's more likely to shatter. As well, you probably shouldn't have a whole kilogram coming down and forcing on the bottom of that. But in any case, for our test, this is enough data that we need. Let's go to the computer and let's take a look at some of these charts. Alrighty, so we're looking at a high quality bearing, 1150 RPM motor with the single strung system. So let's go ahead and get a baseline. Okay, we're looking at baseline of about 0.68 with no load on this. But here's where the real test is going to come. We're going to go up to about 500 grams here. So we got 500 grams loaded up. Let's go ahead and get a baseline here. It's like we're looking at about 0.74. Let's go ahead and move it up to a kilogram. All right, we got a kilogram loaded up here, so let's take a look. I'm only going to run this one once because I'm concerned about the integrity of my final spot here. Okay, sitting at about 0.94 seconds. With all the testing out of the way, let's go ahead and take a look at the data. Let's get started at looking at our final data here. Our low quality is going to be in blue, and our high quality is going to be in green. We're going to look at the 435 motor on the dual strung system. So we can say that when we look at a dual strung system on a 435 motor, there actually is a pretty significant difference, especially when you start getting under load when you're looking at low quality versus high quality bearings. There's not a huge difference when it comes down to a no-loaded system, and in fact, it looks like the low-quality bearings actually outperforming the high-quality bearing, but that one is maybe due to perhaps battery charges and the slight voltages between some of the batteries that I'm using. It could also just be the standard deviation of those tests. But when we look at the overall trend line, in general, that high-quality dual string does actually make quite a bit of difference, especially on those high loads. When we look at the single-strung system, there's actually not a huge difference between the two. For instance, the high-quality single string actually seems to be underperforming the low-quality single string, and that's likely, again, due to some of those variances in that test over time. Could also be due to the variance or the differences in the amount of tension I have on the system, because I have no way of verifying just how much tension is outside of the standard guitar string pull. However, when we look at that high-quality strung dual strung versus the single strung, looking at the trend line from the dual strung and that single strung, it probably doesn't make a huge difference in the single, but it makes a pretty dramatic difference in the dual, so much so that there's actually no functional difference between these two systems when you look at a high quality bearing on a 435 motor. So for instance, in red is the high quality dual strung, in yellow is the high quality single strung, and we're looking at 0.06 milliseconds between the two. That's effectively no difference. So on a 435 motor, using a more compact system like a dual strung system and high quality bearings, it really makes no difference. And what's interesting is that actually makes quite a bit of change to the last experiment we did, where we did compare those two, the dual versus single strung systems. Now, when we come up to the 1150 motor, it starts to make an even more dramatic difference. So on the 435, there wasn't a huge difference in the improvement, but on the 1150 motor, there's a huge improvement when it starts to come getting under sort of really straining loads. If we look at that low quality string for the dual strung or on the blue versus the high quality bearing in green, it almost doubles the effective speed on an 1150 motor. So these high quality bearings really do make a difference, especially when you're starting to get under heavier loads where you have a lot more torque being applied to this system. Why might that be the case? Likely because those high quality bearings have a lot less friction in their rolling resistance. And what that is going to do, well, obviously it speeds things up significantly, especially on a dual strung system, because you have to go through twice as many pulleys. If we look at the single strung system, there's not as much of an improvement. There's still a pretty consistent improvement with the high quality bearing for this low quality bearing, but it's a little bit less. However, when it comes down to the high quality dual strung versus the high quality single strung on an 1150, there's effectively no difference. You're talking about 0.02, 0.06, 0.05 differences between these two systems. You're really not getting much of a difference in the amount of friction and the speed that these systems are doing. So when it comes to my recommendations of what do we do with this data, should you use a single strung floating retraction string system or should you use a dual strung system? Again, it really comes down to what is the benefit of your system. I think in general, I'm going to recommend using a dual strung system. It just makes things way more compact. It's way easier to, well, it's a little bit more difficult to string, but once you have it strung up, it's way more consistent over time because that floating string tends to lose a lot of that tension over time and things like to fall off pulleys. However, using that dual strung system lets things stay a lot more compact, a lot more constrained. You don't have to fight with strings in other places. That said, it's going to depend on individual design. Maybe having a floating string retraction that moves on to another section is more beneficial for your design. But I think in general, using some high quality bearings really do make a significant difference, especially if you're going to run a dual strung system. So if you found these experiments helpful, it really does take me a lot of time to go through this, and I would appreciate if you can give this video a like and consider subscribing for some more robotics content. I hope you can use this data to improve your robotics projects in the future and make your team a lot stronger and better when it comes to performing on the field. Best of luck on your next robotics project.